Hi everyone, in this video we will be covering chapter 4.4, adding and subtracting fractions with common denominators from the OpenStax Pre-Algebra textbook. In this lesson, our learning objectives are to model fraction addition, add fractions with a common denominator, model fraction subtraction, and then subtract fractions with a common denominator. Now I first want to start off with these two questions to ponder. What is the meaning of common denominators? And two, how is this concept important when adding and subtracting fractions? So I'd go ahead and pause the video here and see if you can answer these two questions to start. So first off, what is the meaning of a denominator? So if I was to define a fraction once again, a fraction looks something like this, where I have a top number followed by a fraction bar and a bottom number. Now the top number is what's called a numerator. Now a numerator tells us how many parts of a whole we actually have, while the bottom number is our denominator, and this is telling us how many wholes or how many divisions the whole is sliced into. So for example, 1/2 of a fraction, if I draw a very badly drawn circle here, a half of a fraction, let's pretend those are two even divisions now. This would be filled in right here, right? So that is half of a fraction. Now a common denominator means you are comparing two or more fractions. So for example, if I have a half and let's say another half, these two fractions are now in the same denominator. They have a common denominator of 2. Or if I was to say, let's say I had a fraction 1/4 and 2/4. These are also in common denominator form. Now, how is this concept important when adding and subtracting fractions? Well, this is basically our first step. When we add and subtract fractions, we first need to find or have a common denominator. And the reason for that is this puts our fractions in the same size slice here. Now to really illustrate this concept, I've started with this fraction addition type problem where we're modeling these out using some visual representations here. So we are going to add 1/4 plus 2/4 using this model here. So right now our fractions are over a whole are in fourths, right? So the bottom number tells us the size of the division. So we see these in fourths. The top number then tells us what we have. So 1/4, we'll go ahead and illustrate here, would be where I was to fill in this size slice here. While 2/4, we'll go ahead and put over here, would be me adding this number or this slice and this slice here. So when I go to actually add these, we are just combining or adding our numerators, 1, and we're adding the other numerator of 2. So then when I added both of these together, I get a fraction that is in 3/4 form, which is what this looks like right here. So this is 3/4 of a fraction over here. Now, key thing to note here is when they're the same size slice, when you have the same denominator, you're adding your numerators and then you're writing the sum of that over the same denominator. Now I can also ask myself, can I simplify this down? In terms of 3/4, I can't. So this is simplified as far as you can go. Looking at another example here, we have 1/8 plus 3/8. The denominator is 8, letting us know that there are 8 divisions within our whole here, which you can see represented in the picture below. Now, the 1/8 part tells us that we have one slice for this first fraction, which we can fill in here. Then the 3/8, the other fraction, lets us know that we have 3 slices that we can fill in here. So when we go to add these or combine them, we're going to get 4 total slices, right? So that one slice there, and then the 3 other slices are below this. So modeling this out, or just finishing this with arithmetic, we would add our numerators. 1 plus 3 is 4, and we would keep the same denominator of 8. Then the question becomes, can you simplify this down? Can you simplify 4 eighths here? Well, if you look at the visual representation here, what does that actually look like? If I was to take out some of these divisions, well, you might recognize that, this looks like a half, right? And that's true. So if I was to divide 4 and 8 down below, what this actually becomes is I can divide both the top and the bottom part of the fraction by a common factor of 4. So 4 divided by 4 is equal to 1, and 8 divided by 4 is equal to 2. Or if I show more of the textbook structure, if I go back to the OpenStax textbook, how they like to show it is with common factors by doing prime factorization for both these numbers. So if I did the prime factorization of 4, the prime factorization of 4 is 2 times 2. 2 times 2 is 4. And the prime factorization of 8 is going to be 2 times 2 times 2, right? So 2 times 2 times 2 is 8 as well. Then I look at what are the common factors that I can eliminate. Well, I have a 2 and a 2. I have a 2 and a 2. And then I just have a 2 that's left over in the denominator. Now, also I should note there is an implied 1 in the top number. It can't just be 0. So again, if I look at what I actually now have, I just have a 2 and I have a 1 on top. So this actually simplifies down to 1/2 here. Okay, so either structure, if I look at what 2 times 2 is, by the way, that is actually that 4 there. That's that division of 4. So either structure is good for simplification. Okay, so now let's go beyond the model and let's just look at doing this symbolically, right, with regular numbers here. Okay, so we have 2/9 plus 1/9 here to start. Now, the steps that we are going to follow, our process or algorithm, is going to be to add our numerators, place the sum, which is the answer to step 1 basically, over a common denominator, simplify if necessary, and convert to a mixed fraction if possible, meaning if the number is, if it's an improper fraction when we actually solve it, okay? So in this case, because we have a common denominator, we're still not needing to change the denominators. So all we need to do in this case is add our 2 numerators. So 2 plus 1 is 3, and our denominator is then of 9. So we placed our sum of 3 over a common denominator of 9. Now I'm able to actually simplify this, right? A common factor that goes into both 3 and 9 is that common factor of 3. So I can divide 3 here and 3 here. And what I end up getting is 3 divided by 3 is 1. 9 divided by 3 is 3. Now again, if I want to show in more of that textbook structure, and I did the prime factorization of 3 and 9, 3 is really, I'm going to start with a 1 here. So 3 is really 1 times 3. And 9 is really 1 times 3 times 3. So if I then go and eliminate my common factors here, I can eliminate, keep the 1s, we don't eliminate the 1s. We can eliminate this 3 and this 3. And now we're just left with the 1, 3 left over. So if I rewrite this, on top, I just have the 1. And on bottom, 1 times 3 is 3. So 1/3 is my result. Now, you might ask again, why does the textbook, or why do we want to do it like this? Well, this is actually a great skill to know and understand as you start to go into more algebraic topics. So a great example of this is if you're factoring something called a trinomial, right? Or factoring the greatest common factor out of something. Understanding prime factorization can be a very useful skill. Now, the other step, step number 4, is can we convert this to a mixed fraction? Well, 1/3 is a proper fraction. How I know it's a proper fraction is the top number 1 is smaller than the bottom number 3. So 1/3 is our result here. Okay, let's go to question number 2 now. So question number 2 is 7/10 plus 4/10. So first step here, we will add our numerators. Step 1, 7 plus 4 is 11. Step 2, we're going to place the sum over the common denominator. So 10 stays our common denominator. Now, 11 over 10 can actually not be simplified. How I know that is 11 is a prime number. The only factors of 11 are 1 and 11, so 1 times 11. And if I did the prime factorization of 10, that would be 1 times 2 times 5. Do you see how there are no common factors other than the number 1 itself? Since there are no common factors, that means it can't be simplified. But 11 and 10 can be converted to a mixed fraction. Now, the model I do to show mixed fractions is the long division model. So we can take the numerator 10 and divide into the denominator 10 and divide into the numerator of 11. So 10 goes into 11 one time. 1 times 10 is 10. 11 minus 10 then is 1. 1 goes into our numerator, and our denominator stays 10 at the end. So our answer then in mixed fraction form is 1 and 1/10. Okay, so question number 3 is interesting, right? Because of this, question number 3 has a denominator of x. So you're like, okay, what does that mean? Well, remember this is just a variable, stands for an unknown number, and since it's the same letter, it would represent the same variable. So in other words, we already have a common denominator in this case. So we'd actually follow it in the same exact manner. We would add our two numerators, 8 plus 3 is 11, and then we would keep the same denominator. Step 2, place sum over common denominator, which is x. So now we have 11 over x. Can we simplify this? Well, if we're going to simplify, we need a common factor. Well, the factors of this, again, this would be 1 times 11. And for x, theoretically, this is just 1 times x in a sense. And we don't know what x happens to be. If x was a 11, then you could factor it, but since it's an unknown and there's not another x variable above, we can't actually do anything with that. Likewise, if I was to rewrite 11 over x, I don't know if this is an improper fraction or not. There's nothing to tell me that it is. If the x was smaller than 11, if it was 11 over 10, then yeah, it's an improper fraction, but it's an unknown. So the only thing we can really write this particular fraction as is just simply the numerator 11 over our x variable here. Now let's look at part 2 of adding fractions with common denominators. So some more unique type questions that really are dealing with negative numbers, negative integers in a sense, that you can find in a previous chapter of OpenStax. So let's start then with our first question here. Negative 5x over 7 plus 3x over 7. So the main thing to identify in this, a couple of main things, we have a common denominator. The divisions are already 7. Perfect. We also then have numerators that have similar variable parts, 5x and 3x. So since these are similar variable parts, we can actually combine them. We can add them. Then the next thing to note is we are really just combining the coefficients. To define a coefficient is the number next to the letter. It means when your number next to the letter is really a multiplication relationship. So these coefficients, negative 5x and 3x. Now, to simplify this, we are just paying attention to those numbers. And in reality, if I was to rewrite what I'm really doing here, I'm doing negative 5 plus 3. So I often, when I see this kind of fraction, if I haven't seen it before, I like to just rewrite what we're really solving or simplifying, which is the negative 5 plus 3. So if I go to my number line and I model this on my number line here, -5 starts over here. It's on the other side of 0, right? We're then adding 3. So if I think about this like money, if I have -$5 in my bank account, and then I add $3 to this, I'm going to the right 3 particular units. I'm increasing by 3. Now, 3 is not enough to get to 0, and it's not enough to go into the positives, right? So I'm really going back 3 units, which is -4, -3, and -2. So my answer in this case is -2. So -5x plus 3x, we can rewrite as -2x. That's step number 1, adding our numerators. Step 2 then, we place the sum over a common denominator, which is 7. Now in this case, 2 and 7 also does not have a common factor. If I was to rewrite my common factors, really this is going to be equal to -1 times 2 times x. Those are the factors that are in the numerator. And then in the denominator is actually not, well, I guess not a -1. We don't want to put a -1 there. Is going to be a +1 times 7. And there's no x. So in other words, there's no variables that you can combine. So this is as far as I can go in this case. This is also a proper fraction. The top number is smaller than the bottom one. Okay, so that is question number 1 here. Question number 2 then is -1/4 plus a -2/4. So again, the trickiest part about this is really this is an integer problem. We have a common denominator, and then we have different numerators. So if I was to isolate what I'm doing here, adding the numerators, really this is going to be -1 plus a -2. So what does this mean? Well, again, I like to model this on the number line to start. If I'm at a -1, and then if I add a negative, adding a negative is the same as subtracting a positive. So if I apply this to money again, adding a negative is like charging your credit card. You're adding debt to a credit card. That means you're decreasing your initial starting spot. You're going back 2 units in this case. So I'm going back 2 units from here, and I end up at a -3 here, okay? So this part is equal to -3. So if I then go and rewrite my fractions up here, what I end up having is a -3 is my numerator. And then I'm placing that sum over a common denominator. That common denominator is 4 here. Now, I ask myself, can I simplify? Well, the factors of 3 is a prime number. That's just 1 and 3. And the factors of 4 are 1 times 2 times 2. Again, none of these are common, right? So I can't eliminate any of those. So my final answer is going to be -3/4. I also, just to clarify, can't convert it to a mixed fraction because this is currently a proper fraction, right? Proper fraction, numerator smaller than the denominator. Okay, let's look at question number 3. This is interesting as well because we have 3 fractions in a row here. We have 5/12 plus a -1/12 plus, I should probably keep this more even, -3/12 here. So again, notice the denominator is the same. So luckily I don't have to change anything with the denominator. That's already the same. So really all I'm doing is adding my numerators, and this really is just, again, a integer type problem. So I have 5 plus a -1 plus a -3. Okay, so I like to do this in chunks to start. So if we think about what this actually means, let's say you have 5, so that's a +5 on the number line. Again, if I think about it in terms of money, I have +5. I then am adding a -1. So adding a negative, That's like charging your credit card. That's the same as subtracting a positive. That decreases my overall starting spot. So I decrease it by 1. If I decreased it by 1, I'd end up at 4. So that first little part here, I'm moving back 1 unit to 4. I then am doing the same thing when I'm adding -3. So again, I'm charging my credit card another $3. So I go back 3 more units, adding a negative. And where I end up at that point is at a +1 here. Okay? So 5 plus -1 plus -3 is really 5 minus 4 in a sense. There's 4 total units that you're taking away. So our answer for the numerator then is 1, +1 as well. That's the step number 1. Adding our numerators is step number 1. We get +1. We then place the sum over the common denominator. Our common denominator is 12. I can't simplify. I can pretty much know that without even having to show the factors out, because when you have 1, 1 can't be simplified further. It's also not a mixed fraction. It's a proper fraction. The numerator is smaller than the denominator. So 1 over 12 is my result here. Now let's model fraction subtraction, starting with this particular statement. 4/5 minus 1/5. So again, our fractions, our wholes, are divided into fifths. You can see that in the images below. So this first particular fraction, we would then fill in with 4 slices. So we have 1, 2, 3, 4. And then the other fraction, what we are taking away in this case, is 1. So in reality, when we go to subtract, we're eliminating this slice from here and here, and the amount of slices we then have left over at the end will be 3. So if I have a common denominator of 5 already, all I need to do for subtraction then is to subtract those numerators. So I get to 3/5 here. Another problem that's like this is the following here. So 7/12 minus 2/12. Again, notice that we now have divisions of 12, so it's a bigger division. We would start by filling in our 7 total, 1, 2, 3, 4, 5, 6, 7. And then we are taking 2 of those divisions away. So I'll take these 2 here. So then if I went to write in the slices that we have left, we would be in here, 1, 2, 3, 4, 5 is what we have left over. Okay, so 5/12 is my result. Okay, so this is the visual representation, the visual model of doing the subtraction. Let's go ahead and now go to a process that we can apply. So the process that we can apply here, very, very similar to the adding of fractions process we talked about earlier, just with subtraction. So if I start with my first question here, 5/6 minus 2/6, and I notice that I have a common denominator already. All I need to do in this case is subtract my numerators, 5 minus 2, which is 3, and then keep the same denominator, which is 6. So that's step 2. Place the sum over the common denominator. And actually, I should say it's really the difference. It's probably a better way of saying that. Place the difference, total, 3 over 6 here. Step 3 then, simplify if necessary. So I have 3/6 here. In this case, I can simplify, right? If I was to, well, I'll go ahead and do both. So if I divided it, I can realize that, a 3 divides evenly into both. And I now get 3 divided by 3, which is 1, and 6 divided by 3, which is 2. If I show more of a textbook structure, I was going to say Facebook, textbook structure, what this looks like then is to actually rewrite our numbers in prime factorization. Well, 3 is already a prime number, so this is 1 times 3. And 6 really can be written as 1 times 2 times 3. So the common factor here then is that number 3. So I can eliminate that, and then what I have, if I was to basically multiply, I have 1 just by itself, and then I have 1 times 2, which is 2. Okay, so in both cases, 1/2. So this is now simplified. This is also a proper fraction, which means I cannot convert to a mixed fraction. So that is my result there. Okay, going to question number 2 now. This is interesting because I have 2/9 minus 7/9. I have a common denominator, but now I have a bigger total on the other side. So occasionally when you didn't know about negative numbers, you might be like, well, I can't do this, right? You can't subtract 7 from 2. Well, yes, you can if you have negatives. If you think about money, you can go into debt. You can spend more money than you have. So if I was to really, again, model what I have 2 minus 7 here. That's really what I'm looking at. So if I go to my number line and model this on the number line, I'm starting at positive 2, and I'm going back to the left 7 units here. And when I go back 7 units, I end up at a negative 5. Okay, so negative 5 is my result from subtracting my numerators. I then place this difference over the common denominator, which the common denominator is 9. So I now get 5 over 9 as my result. I can then ask myself, can I convert this to a mixed fraction? In this case, 5/9 is a proper fraction. It's not a mixed fraction, or not an improper fraction, so I can't convert it. So this is my result here. Question 3 then is going to be 9z minus 4 over z. Now again, like the previous one, z is a common letter, means a common number, so that is a common denominator already. I don't know what it is, but I can combine my two numbers here. Now, if this was a different letter, I wouldn't be able to combine it, just to let you know. So 9 minus 4 then is 5. Place the sum over a common denominator of z. Now 5 over z, there's nothing really to simplify here. There's no coefficient with a z that I can do. I can't convert it to a mixed fraction because I don't know if it's a mixed fraction. Don't know what the z is. So this is as far as we can go. Now let's do part 2 of subtracting fractions with a common denominator with some more unique questions like the previous types of problems. So let's look first at negative 3/5 minus a positive 4/5 here. Okay, so now what we're going to do is recognize we have a common denominator. So we're just going to subtract our numerators here, which I like to isolate just as kind of a regular whole number or integer fact. So if I have negative 3 minus 4, and I'm to think through this on the number line, I'm starting at negative 3, which negative $3. I then am subtracting a positive 4. Subtracting a positive is like you spending more money. So you are decreasing your overall value by 4 units. You're going more in debt, in other words. So you're ending up at a negative 7 there. So this becomes a negative 7. And then you keep, let me actually bring this down a bit. I'm going to erase this part. Let's bring it down. So we have a negative 7 over our denominator of 5. Now, I can't simplify negative 7 over 5. Both of them are prime numbers, so they don't divide into each other in this case. So what I can do, though, is I can recognize that, this is an improper fraction, right? The top number 7 is bigger than the bottom number 5. So I can divide a 5 into 7. 5 goes into 7 one time. 1 times 5 is 5. 7 minus 5 is 2. 2 is now a numerator. And my denominator stays 5. Now this was a negative here to start, so it does become a negative at the end. So in other words, my mixed fraction is negative 1 and 2/5 here. Going to question number 2 now, I have negative 4 over 11 minus negative 2 over 11. Again, I notice that they are a common denominator, so then I can really just isolate and subtract the numerators. So there's a lot of negatives here. I have negative 4 minus a negative 2. A lot of negatives. If I go to model this on my number line, the number I'm starting with is negative, so I'm starting at negative 4. But now I'm subtracting a negative 2. Well, subtracting a negative is the same as adding a positive. If I think about it in terms of money, subtracting a negative is like you subtracting away debt. It's you taking away some loan that you had. So because of that, that's increasing your value. So you're increasing your value by 2 units, or $2 if you think about it in terms of dollars. So if I go back $1, it's negative 3, or 1 unit, negative 3. Another unit, I then end up at a negative 2. So negative 4 minus a negative 2, your answer becomes a negative 2. Now, by the way, you could rewrite this if it makes more sense for you to write it as negative 4 plus 2. Subtracting a negative is the same as adding a positive, so adding a positive 2 here. So I have a negative 2 on top. I then write this sum, or the difference, over a common denominator of 11. So I now have negative 2 over 11. I can't simplify 2 and 11. 2 and 11 are both prime numbers. The only factors are it's themselves and 1. It's also not a proper fraction, so I can't convert it, or excuse me, it is a proper fraction. It's not an improper fraction, so I can't convert it to a mixed fraction. So negative 2 over 11 stays like that. Question number 3 now. I have negative 5r over 9 minus a positive 3r over 9. Okay? Notice the common denominators. This means I can just isolate my numerators. So I have negative 5r minus a positive 3r. If I go to model this on my number line, I'm starting at negative 5. In this case, I'm just going to go ahead and really look at the coefficients, the numbers in front of the variable here. So the negative 5, I'm now subtracting away a positive 3. Subtracting away a positive, same as adding a negative. In both cases, you are decreasing your value by 3 units. So I'm going back to the left 3 units. I'm spending money, I'm going more in debt. So I end up at a negative 8. So negative 8 is now our answer for the numerator part. I then place my sum over a common denominator of 9. I then ask, can I simplify negative 8 over 9? Well, negative 8 is not a prime number. So and 9 is not a prime number. So if I write my factors of 8 and 9, just to see if there are any common ones, the factors of 8 are 1. And if I do the prime factorization, it's 2 times 2 times 2. So 2 times 4 is the composite part of it. And if I break up 4 into 2 and 2, you now have that. So 2 times 2 is 4, 4 times 2 is 8. If I do 9, the prime factorization of 9 is 1 times 3 times 3. 3 times 3 is 9. Notice that none of these are common factors. So because of that, negative 8 over 9 cannot be simplified. So that's as far as you're going to go on the simplified part. You can then ask, can I convert it? And you can't, right? So negative 8 over 9 is a proper fraction. The top number is smaller than the bottom number. So that is as far as we can go. The last 2 questions I have for us are some word problems that deal with the concepts we have been taking a look at. So now we're looking at a scenario. We're trying to identify some key words to let us know the type of operation we are doing. So question 1 is, Maria drank 2/8 of a bottle of water in the morning. So if I was to draw, let's can't really draw, so we'll just draw something like this. So she drank, we'll say 2/8 of a bottle of water and 4/8 of the bottle in the afternoon. Okay, so she drank another 4/8 here. What fraction of the bottle did she drink all together? So basically this means that this is the 4/8 part. All together means you're totaling it or summing it, which is addition. So in reality, what you're doing is you're doing 2/8 plus a 4/8. That key word is all together. This means to add. Okay, so I've kind of modeled out what we're looking at. We didn't drink this part of the bottle, I guess, but we've drank all that other aspect. So now we have 2/8 plus 4/8. In this case, we're now going to add our numerators. 2 plus 4 is 6. And we write the sum over the common denominator of 8. Now we have 6 over 8. 6 over 8 can be simplified, right? If I was to write the prime factorization of 6 and 8, what I see here is 6 can be written as 1 times 2 times 3. 2 times 3 is 6. 8 can be written as 1 times 2 times 2 times 2. So in other words, we have a common factor of 2 that we can eliminate here. We have this 2 and this 2. So really what we then have here is 1 times 3 is 3. And 2 times 2, or 1 times 2 times 2 is 4. So 6/8 reduces down to 3/4. This is more of the textbook way of showing it. The other way to model it, which is really the same exact thing, but looks a little different structurally, is we are going to divide both the top and the bottom by that even number 2 here. So 6 divided by 2 is then equal to 3. And 8 divided by 2 is then equal to 4. So again, same structure there. Good to know both. All right, question number 2 then. Jordan had already saved 7/10 of the money he needed to buy a new laptop. So we're buying a laptop here, and then he is saving some money. So obviously to buy the whole laptop, there's some money involved, dollar bill. He saved 7/10 of what he needed for that laptop. So essentially then he needs another 3/10 to get to the overall amount. But then he used 2/10 of the laptop's total cost to pay an unexpected bill. So basically he sliced away some of that money, 2/10. What fraction of the laptop's total does Jordan still have saved? So in other words, in this case, he started with 7/10, but then he spent some of this money on a bill, which was 2/10 of it, okay? So now we are subtracting our numerator, 7 and 2, which is 5, and writing that over a common denominator of 10. So now I have 5 over 10 as my result. Now 5 over 10 can be reduced. If I look at the factors of 5, 5 is a prime number, 1 times 5, while 10 is 1 times 2 times 5, right? In other words, our common factor that we see in both the top and the bottom parts are of 5. So what I then have here is I have 1 in my numerator and 1 times 2 in the denominator. So again, I get 1/2. The other way to structure it again is if you didn't want to expand this out, you could simply show it with a division symbol where we are dividing both the top and the bottom number by that common factor of 5 here. So we end up getting 5 divided by 5 is 1, 10 divided by 5 is 2. So 1/2 in both instances. All right, so those are our 2 word problems. This then ends our presentation. So again, our learning objectives for this lesson was to model the fraction addition. So we used some visual representations to model that fraction addition. We then added fractions with common denominators. We modeled fraction subtraction. We then subtracted fractions with a common denominator, and we applied all of that in the context of a few word problems. So I'd go ahead and get into the OpenStax chapter 4.4, do a few more problems from the textbook. If you do have any questions, feel free to drop it in the comments. Happy to answer them as I'm able. Otherwise, good luck, and I will see you guys in the next video. Thank you.